Hello everyone, I am Srimanti and I am currently working as an ML engineer. Today we are going to discuss one of the most important machine learning topics, which is dimensionality reduction. We are going to look into some common algorithms which are like principal component analysis or PCA, and we are going to learn how and why we do this dimensionality reduction. And we're going to take some examples and show you the math. Let's break down the math so that you can understand the coding and you can understand the math and derivations easily. Great. So now that we have that out of the way, without any kind of further ado, let's start. So many kind of machine learning datasets that we have, that we see in our real life, they all have millions and thousands and hundreds of examples of features. Not like the normal house prediction ones, the ones that are like very complex. For example, stock prices, which keep on changing at any point of time. So many HFTs are just fighting to get the best benefits and the best profits. So these all have millions of features, obviously. So often in this case, the training becomes very, very slow and inefficient. So what can we do to reduce the dimensionality when we have such a large data set? We can just remove some of the features randomly. We need to have a proper direction. So that is where the dimensionality reduction comes into play. For example, let's consider the MNIST dataset. We know that it has so many handwritten images, like digits that we generally see, and we try to classify them, right? So these MNIST dataset that we have, it also has so many features. But now if you think carefully, very, very carefully, the ones that are on the borders, as you can see right here, the ones on the borders, these are all white. So we can as well remove them easily, and still we would have so much dimensionality left, and the accuracy would not be affected much, right? So that is why here we can try to optimize our training and make it faster and reduce 70% of the dataset if we just remove the white borders of most of these images. Also, some of the images where the black borders are very, very close together, we can actually take, not consider two ones separately, we can take them as a single one. So these are some of the optimizations. If we are done properly and through a proper route, you can actually get great benefits. And also, this is obviously, since it's so important, it's also a very favorite topic of the interviews. So let's focus on this now that we know why we're trying to do this. Okay, so now why would dimensional reduction work in general cases? So mostly when we are dealing with a very high dimensional space, so most of these training instances, they are not actually uniformly distributed across the entire space, because consider a very high dimension. So then there's so much space. Obviously, we don't have the training instances distributed exactly thoroughly across all the spaces. It is very practical to think that they will be congregated in one place. So that is why this has been observed like over statistics of many examples. So that is why we are going to use that to our benefit. What we are going to do is we are going to map that down to a very lesser dimensional subspace and still capture most of the variance of the data. Let's take an example. As you can see right here, we have an example of so many points that are actually, if you look very, very carefully, you can actually see that they are very closely linked to a 2D plane. So if you can see that this is actually a 3D space, right? But the points are distributed such that they appear to be lying very near to a plane. So that plane we can actually deal with, and we'll get like a very high accuracy, like whatever was achievable in the 3D space. Not exactly that, but very close to that. And still, our training will be so much faster and so much easier. Exactly, we have now just reduced our 3D dataset to a 2D one and still capturing all the values. One more very cool example is the Swiss roll. So as you can see right here, this is an example of a Swiss roll dataset. So if we project it directly, then you will see that the dataset is not exactly capturing the entire variance. But if you unroll it, see like this, and then you are able to project it down here like this, so then you actually have a very good dataset, and it's all in a plane. You have converted from 3D to 2D successfully. So this is very important as well. Now we're going to discuss the PCA, which is the principal component analysis. What does it mean? The principal component is the one that we're trying to find. So what is this principal component? It's actually the axis. Remember this, it's actually the axis of the dataset where we have captured the maximum variance. For example, let's consider this. This dataset, as you can see right here, there are three different kinds of axes that we can take the data against, right? So this dataset has this axis on which it has the maximum variance. So that is our first component or the principal component. The next one is the second dataset, which it does not have much variance captured. And the last one is very little variance captured. So obviously the one which has the largest variance captures the most features about the data in 2D space when we are converting from 3D. So that is why we are going to use that. Very simple logic, right? You're with me so far? Very good. So this axis is also called as the first component, as I said. Why? As there is another definition for this axis as well. The one that is having the minimum difference between the variance of the original variance in the dataset and the final variance when it's projected onto that axis. So that is the mathematical definition and the one that we are going to use. Now, after we have found out the first principal component, our work is 95% done. Now what we are going to do is we are going to take the one axis which is orthogonal to this one, and we are going to get the variance along that axis as well. So let me try to break it down. So we have a 3D data set, right? So now this axis is the one along which we have the max variance. So that's the first component. Now we are going to take the one that is orthogonal to this, which is this axis, and we're going to take the variance of that axis. So now we have two axes compared to the three axes that was earlier, and these two axes capture the most amount of variance. Get my point? So from 3D to 2D, we're coming back. So like this, whenever we are coming from n-dimensional space to suppose we're coming to d-dimensional space, so d could be n-3, could be n-5, could be n by 2, whatever it is, we are going to go step by step. We are going to take the axis one by one. The one along which there's the most variance, then the one along which we have second highest variance, which is orthogonal. That is also very important, not like any axis. Which has the next second amount of variance, again orthogonal to that, which has the third highest variance, and so on and so forth till we get the d dimensions that we are looking for. This is just the very crux of the intuition behind dimensionality reduction, and there you have it. It's very, very simple. Now let's draw that on pen and paper. So we are going to use here a standard matrix factorization technique, which is called singular value decomposition, or SVD. So as you can see right here, this is the formula for SVD, and this V contains the unit vectors that define all the principal components that we're looking for. See, it's very, very easy. You can just put it into any kind of software, and the software will give you the V. We'll see as soon as possible in this video only. So stay tuned. Do not go away. So this is what the SVD matrix looks like. One more thing which is very important, as we will see right here, is that the PCA requires the data to be centered around the origin. So if you're using a PCA from scikit-learn, then you don't need that. But if you're doing it manually from scratch, then you need that. For example, as we'll see right here, this is the piece of code that you need to remember. Write it down, note it down, and use it next time. I'll show one example that we'll soon do here. Some phase image segmentation that we're going to do using PCA. So stay tuned. MNIST dataset also we can use PCA there. I'll show you that as well. We'll come to that. And after this is done, the way you will get we have the vectors. Now we just need the dataset, final dataset, that is a reduced dimensionality dataset. So this is the formula for that. And very simple, this projection, and we already have the vectors. So it's just a piece of cake. And yeah, there you have it. You have the dataset finally. So we'll do that on MNIST dataset, and it will actually reduce it by 70%, which is a huge, huge benefit. There you go. We have covered the PCA in its entirety. Some of the examples, some of the extensions of PCA we'll soon cover. For example, randomized PCA, kernel PCA. But till then, all the best. This is what is needed for your ML roadmap. And yeah, you have it. You've covered it. You deserve a round of applause. I'm really proud of you. Let's go. We'll see you in the next video. Till then, take care. Bye-bye.